Okay, what we're going to learn about today is projectiles. And projectiles is going to put together the pieces of information that we have learned from vectors and from kinematics. A projectile is something that is moving through the air where the only force that's acting on it is that of gravity. So if you think about a baseball being thrown, once the baseball leaves your hand, whatever forward momentum you have given it, it's already done. You can't give any more momentum or any more force to it after it leaves your hand. So after the object leaves whatever it was in contact with, whether that was your hand or a table or something like that, then the only force that remains is that of gravity. There are two possible launch configurations that we'll learn about. The first one is projectiles that are horizontally launched from a height. So, like a ball that is rolling off of a table. So it initially leaves the table horizontally, and then it falls to the floor as it travels outward. Let's label some things about this picture. First, we know the height of the table. Second, we can measure how far out in the x direction the ball travels, and we call that dx, distance in the x direction or the range. And then we can measure some things about the ball's velocity as it travels through its path. First of all, the velocity in the x direction remains the same throughout the path. That's because after the ball leaves the table, whatever forward momentum or force it had in order to leave the table, that force is finished once the contact between the ball and the table is over. So if there's no force, there's no acceleration, then the velocity has to remain constant. So we'll make a note of that off to the side. The velocity in the x direction has to be constant throughout the path because there is no force in the x direction. If we look at the y direction, at the very beginning of the path, at that split second where the ball rolls off the table, the velocity in the y direction is 0 because it hasn't yet begun to fall. And then as gravity accelerates it downwards, the velocity in the y direction would increase. So we'll make a note of that too. The velocity in the y direction is increasing due to gravity. Now, what equations can we apply from kinematics to this situation? We have two parts to our information, or two parts to our velocity. We have to deal with the things that go in the x direction and the things that go in the y direction. So for the x direction, we really only need one equation because velocity is constant in the x direction. That means we only need the equation that goes with constant velocity. So that's distance equals velocity times time. Notice that we've included little x's now to indicate that this is the distance and the velocity in the x direction. In the y direction, our object is essentially in free fall because whatever force was applied only in the x direction, and that force is over once the item leaves the contact of the table or your hand. And so after that, the item is essentially in free fall in the y direction. And so we have height equals 1/2 gt squared, and the velocity in the y direction equals gravity times time. Let's look at our second configuration, launched at an angle. If you have a projectile that is launched at an angle, you have an initial velocity at that angle. But this is a vector. So we know that that velocity has two components. It has an x component and a y component. So find Vx and Vy first. So Vx goes in the x direction. And because of our trigonometry, our triangle, we know that Vx equals the initial velocity times the cosine of theta. We also have the velocity in the y direction, and Vy equals the initial velocity times the sine of theta. Always check your triangle to be sure you have the right trig functions, but for the most part, Vx is cosine and Vy is sine. Let's label some things on the path that this projectile would travel through. So we have our initial velocity and our initial angle. And you might know that projectiles typically travel in a parabolic path or in the path of a parabola. We can use that to our advantage because we know that parabolas are symmetrical on both sides. I'm going to put the ball on the path at some strategic points. Notice that they are across from each other, so there's a mirroring point on the other side. And we'll start labeling. We know the range or the distance in the x direction. We could find the height. Notice now that the height goes from the ground level up to the peak of the path, which is halfway through the path. So if you're looking to find the height, you have to choose the corresponding information. So if you have to plug in time, it would be the time to the peak, or T peak, because it's only half of the time that the projectile's in the air. We can also measure Vx, just like we did before. Vx is constant throughout the entire path, because once that object is flying through the air, whatever momentum or force that it had being applied when it started is over. Once the contact is over and that object is only in the air, the only force that remains is gravity, which is what changes our velocity in the y direction. The velocity in the y direction starts off now as being large, and then as the projectile rises, it gets smaller because gravity is pulling it downward or slowing it down. At the very top of the path, the velocity in the y direction is 0 because that's the split second where it turns around and heads back down. On the other side, the velocity in the y direction would be small at first and then increasing as gravity accelerates it downwards. Projectiles, therefore, behave the same way on the way up as they do on the way down because gravity is the only force that's acting on them, and gravity acts the same throughout the entire path. So you can use symmetrical points on your parabola to help you figure out information that you don't know. And a reminder, on the way up, Vy gets smaller because gravity slows it down. And on the way down, Vy gets larger because gravity accelerates it. Remember that those vectors that are across from each other would be the same size, but pointed in the opposite direction. So they'd have the same magnitude and the opposite direction. Okay, let's make a note. Equations that we use for the y direction would include time equals Vy divided by gravity. And notice that I've included T peak as the time because this is a free fall equation and the item is really only in true free fall on the second half of the path. So you'd be using the time to the peak, which is the same as the time from the peak down because it's symmetrical, so it'd be a halfway time. And if you're asked for the total time that the projectile is in the air, remember that you have to double that from T peak. So the total time equals 2 times T peak, or 2 times Vy divided by g. Another equation that might come in handy from free fall is height equals Vyt minus 1/2 gt squared. This is a variation on the d equals Vt plus 1/2 at squared. And again, you've got to use T peak wherever you're plugging in a height because height comes from the halfway point. That's the highest point, so you have to use the halfway time. In the x direction, we would have our constant velocity equation, dx equals vx, but you have to make sure you use the total time because that would be the total range.